everyone. It's a great honor for me to introduce Professor Stefan Rahmstorf, who is a co-head of Earth System Analysis Department of the Potsdam Institute for Climate Impact Research and a professor of ocean physics at the University of Potsdam. In his research, he focuses on paleoclimate, ocean circulation, and Earth system modeling, among others. He was one of the lead authors of the fourth IPCC assessment report. He is not only an outstanding and highly cited scientist, but also an excellent science communicator. For his achievements, he received prestigious awards, including Climate Communication Prize of the American Geophysical Union. So please welcome Professor Stefan Rahmstorf.
Yes, hello everyone. It's a great pleasure to be here in Barcelona, and I want to give you an overview over the oceans in a changing climate. Please allow me to start with a few general slides on the changing climate before I then focus specifically on the ocean. I always like to point out that the German explorer Alexander von Humboldt already wrote in the year 1843 that humans are changing the climate, quote, by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. He was ahead of his time, I think, with this insight. But now, of course, this is very well known, and the main driver of warming is carbon dioxide. And this diagram shows very clearly how the CO2 concentration in the atmosphere has dramatically increased by about half above the normal Holocene level. And when you look at the year numbers there, you also see that that increase is actually accelerating over time. This increase in CO2 alone causes a radiative forcing of 2 watts per square meter, and that's the reason why the planet is getting warmer, because it is being heated at this rate day and night around the Earth on average, 2 watts of heating for every square meter of Earth's surface. And obviously, if you add heat to a system, it's going to get warmer. This is just very elementary physics. The result is this warming shown here in the famous warming stripes, or more conventionally in a data curve like this. And I think it's very clear that we are in the middle of a very rapid warming, reaching now about 1.2 degrees centigrade above the level of the late 19th century. And we get often asked how much do humans contribute to the modern global warming, and the answer of science is 100%. This is from the latest IPCC assessment report, but very similar diagram was already 7 years earlier in the previous IPCC report. This is independent measurements of the observed warming and estimate of how much human-caused warming there is, and within the uncertainties they agree. And there is also no known natural cause of modern warming. A key factor, of course, affecting the radiation balance of our planet, which sets the global temperature, is solar variability. But the solar activity has declined slightly over the last 60, 70 years, so it has very slightly counteracted the warming that human activities have been causing. So most likely we have actually caused a little bit more than 100% of the observed warming since at least the mid-20th century. On a paleoclimate perspective, we can look at the global mean temperature since the last ice age, here for the last 24,000 years or so, and you see the warming from the last glacial maximum into the Holocene, here by about 7 degrees Celsius, which took around about 10,000 years, and the very stable Holocene climate in which Homo sapiens discovered agriculture and settled down, started to build cities. So we have benefited from 10,000 years of pretty stable climate, but we have now already left the Holocene climate. Global mean temperature is most likely, according to the paleoclimatic data, already warmer than at any time in the entire Holocene. And also this warming happens many times faster than the warming from the last ice age into the Holocene, which is due to those orbital cycles, the Milankovitch cycles. So we are changing climate at an unprecedented speed, and we are really catapulting ourselves out of the Holocene into uncharted waters, into a climate where neither human society nor natural ecosystems are adapted to. This is obviously very dangerous. Most of the heat, and now I come to the oceans, most of the extra heat that is trapped in the Earth system due to that increase in greenhouse gases is ending up in the oceans. 93% of that heat has gone into the ocean. This is not because the oceans have warmed more than the atmosphere. The contrary, the atmosphere has warmed more strongly. But the heat capacity of the oceans, of course, is much, much greater than that of the atmosphere. And directly accessible, the main heat storage is in the top mixed layer of the ocean, but heat is already also penetrating measurably down to several thousand meters depth into the ocean. And so the ocean heat content increase is obviously a lot less noisy than the surface air temperature, and some people have suggested that ocean heat content should be actually a better measure of the amount of global warming than the change in surface temperatures. Because there's a lot less year-to-year variability in it. But on the other hand, of course, the impacts are mostly due to the changes in surface air temperature, the more immediate impacts of global warming. Now, one aspect of ocean warming is the loss of sea ice. This is what the Arctic Ocean looked like just a few decades ago in the summer. This is the kind of sea ice cover there. And in the meantime, it typically in the summer looks more like this. So around about half of the surface area of the sea ice cover of the Arctic Ocean has been lost in recent decades. At the same time, this sea ice cover has shrunk by half in thickness as well. So in that sense, we have already lost about 3/4 of the ice mass floating on the Arctic Ocean in the summer. And I think all the people in this room will still live to see this. This is just a few decades away, a situation where for the first time we will witness an almost ice-free Arctic Ocean. Here again, we can use proxy data from sediments to look at the long-term evolution of the ice cover on the Arctic Ocean, going back about 1,500 years here. And it shows pretty well a steady sea ice cover until the last few decades. The direct observations are the dark blue dotted line there, starting in the 19th century, and you see the very steep decline since the mid-20th century, and the red dashed part, that's the satellite trend since the 1970s. So basically the sea ice cover on the Arctic Ocean is in free fall. And my colleague Markus Rex from Potsdam was the leader of the Polarstern expedition across the North Pole a couple of years ago. And when they came back, he said, we watched the ice dying. Another aspect of ocean warming, of course, is the rising sea levels. And this shows the sea level curve since the year 1900. The blue curve is from the tide gauges in the harbors, and the red curve is the satellite data. And I'm old enough to very clearly remember when I saw the first talks showing the very first few years of the satellite data, which really had quite an impact at the time because they showed immediately an upward trend, confirming that there is a global rise in sea levels. Of course, we sort of knew this from the tide gauges before, but the tide gauges, of course, they're only at the coast. They're at harbors, at best at islands, so nobody before the satellites really knew what is going on in the open ocean. And so it was quite a revelation when the satellite data were basically showing the same as one could already derive by properly averaging the global tide gauge network. Of course, tide gauges are also affected by land uplift or subsidence. There is another reason why the tide gauges don't give us directly the change in sea level. And before the advent of GPS data, also nobody was sure how much the land is rising or sinking anywhere. And that's why these satellite sea level data are incredibly important data set to confirm the general prediction and expectation that, of course, sea level will rise in a warming climate because the ocean water expands and continental ice melts. And that's also the reason why the sea level rise accelerates, because, again, basic physics, the warmer it gets, the faster the continental ice sheets and glaciers melt, and so the faster the sea level rises. And of course, in the first decade or more of sea level rise data from the satellites, we couldn't see the acceleration in the satellite data, but by now, the acceleration also is clear just in that relatively short satellite data set that starts in 1993. The sea level rise actually is not entirely uniform. This is a trend map starting again with the beginning of those satellite data. You can see here 1993. And there are regional differences. I don't have time to really go into the reasons for that. There are, of course, changes in prevailing winds that can change the local sea level. There is an important effect of ice sheet gravity. So if you can kind of see this on this picture here, that around the coast of Greenland, the sea level isn't actually rising. That's because Greenland is melting, and if you have less ice mass on Greenland, you have less gravitational pull of that ice, which pulls the seawater towards Greenland. And so with mass loss, the sea level moves away from Greenland. And that leads to extra sea level rise in the far field away from the big ice sheets and reduced sea level rise near the big ice sheets. Also is happening near Alaska, by the way, where a lot of glacier ice is being lost. So just flagging this, that's an interesting sub-branch of sea level studies, is understanding these regional differences in sea level rise. I've been part of a project looking at sea level for the last millennia from salt marsh data from drilling in the sediments. Here's some field work that we did on the Outer Banks in North Carolina and reconstructed sea level rise for 2,000 years. And this is the change in every century. Sorry, it's an American plot, so it's in inches. So in some centuries, you see 1 or 2 inches of sea level rise, and others 1 or 2 inches of sea level drop. But in no previous century since the birth of Christ has there been anything like the sea level rise in the 20th century, which is again entirely expected because there never was such a warming as we see now. And therefore, why would there be a big sea level rise? There has been, of course, a long skeptics debate, this kind of fake debates that the media love about sea level rise, and people have said, oh, well, sea level has been rising all along for the last 2,000 years, which of course is disproven by the data that I just showed you before from the salt marshes, but it's already before, and it's in one of the early IPCC reports that's already mentioned. It is disproven by things like these Roman fish ponds. So if the sea level had been rising at current rates already for 2,000 years, these Roman fish ponds, they would be submerged under like several meters of water by now. But they have been built exactly to exchange with the tides, get fresh water into the fish ponds, and at low tide empty it out again a bit. There are nice canals. I was visiting this with some local Italian colleagues at one of the PALSI meetings, paleoclimate sea level studies. And yeah, it's just a nice example for showing that this sea level rise really is a modern 20th century phenomenon, and it hasn't been going on for millennia. Today we also have a very clear idea of the sea level budget, at least since the beginning of the satellite data. It is practically close to within uncertainty, so you have independent estimates of the ocean thermal expansion that you can get from ocean temperature measurements, from Argo floats, etc. Independent estimates of the glacier mass loss and the mass loss of Greenland and Antarctica, which are measured by satellites, the GRACE mission. And then all these individual components, they add up to, within uncertainty, the actual measured sea level rise. And the summary is kind of, it's roughly half thermal expansion, roughly half ice melt. And there are some further small components from groundwater pumping for irrigation purposes, for example, or storage of groundwater in dams. But mostly, really, the sea level rise is a mix of thermal expansion and continental ice loss. For the future, the ice loss will more and more dominate because it is much more potential there. And the IPCC estimates between, depending on emission scenario, here about 0.5 meter and a meter by the end of the century. Actually, for many coastlines, that already is catastrophic, especially when it comes up to near a meter. Lots of places already now have big problems with sea level rise, with like the nuisance flooding you get on the North American East Coast just from the normal tidal cycles nowadays already, or storm surges that get a lot higher. If the sea level has risen by 20 centimeters, that doesn't mean a storm surge just gets 20 centimeters higher. There's nonlinear amplification effects there because of reduced bottom friction, for example, when you start out with a higher sea level. And of course, the last centimeters of a storm surge are always the most damaging because they penetrate into areas where you never expected the water to reach during a storm surge. If you think of Hurricane Sandy, for example, that reached a level where it flooded subway tunnels in New York City, then it really gets very expensive, obviously. A new feature in the IPCC report, the last one, is this dashed scenario here, the high impact storyline, as they call it. The American climate assessments have done that already a long time earlier. They simply acknowledge that there is a very one-sided risk towards much higher sea levels because of the lack of proper understanding of the ice sheet behavior. Once the ice sheets start to slide, then you can get a lot faster sea level rise than currently from surface melt. And we cannot reliably model that, but there is this risk that sea level rise could turn out to be a lot higher than the kind of more likely mainstream scenarios shown here. One point I like to point out here, these blue scenarios that we see at the lower end here, these are scenarios where the warming has stopped in mid-21st century. Paris compatible scenarios between 1.5 and 2 degrees global warming. But even though warming has already stopped around 2050 there, the sea level continues to rise, and it will do so for centuries, basically, because what we can prevent by stopping global warming is a further acceleration of sea level rise. But because of the long time scale of ice melt, the rise itself will continue for many centuries to come. And the IPCC also included in the latest report a projection to the year 2300. And even for Paris scenario, it could be up to 3 meters here that we get by 2300. You know, we have 130 cities with more than 1 million inhabitants on the coastlines. You know, how many of those will still be there after 3 meters of sea level rise? Not so many, I would say. And then for higher emissions, it's like between 2 and 7 meters here. And up at the top, the small print says sea level rise greater than 15 meters cannot be ruled out by the year 2300. So very big one-sided sea level rise risk here. And in the long run, here there's been a nice study looking ahead even 10,000 years and also 20,000 years back. We have the experience from the transition from the Ice Age to the Holocene. I showed the temperature rise earlier on, about 7 degrees Celsius, and the sea level then rose 120 meters. So that's this 120 meter sea level rise when the ice sheets melted after the last ice age, and stable Holocene sea level. And depending on emissions, we're getting a very big further sea level rise. The lowest one, that's kind of 2-degree Paris scenario, ends up at 25 meters sea level rise by 10,000 years in the future. This is the very long-term sea level rise commitment which we are causing now. And if people say, well, I don't care what is in 10,000 years, this is the rate of rise here, and the highest rates of rise are, of course, in the much nearer future. So that's where the real problem really will hit us very soon with sea level rise. And if you just look at how much ice there is enough ice on the Earth now on Antarctica and Greenland to raise global sea level by 65 meters. That was illustrated about 10 years ago at the cover of National Geographic there. This is where it would go to the Statue of Liberty if all the continental ice on Earth would melt. And yeah, you don't have to have a scientific study to imagine the impact on a place like this if the sea level rises. The Maldives are building a new island already that is 2 meters higher, where they want to relocate much of the population. That's, of course, not a solution that is open to many coastal places. You have to have very shallow seas there, lots of very suitable sand to pile up a new island, and so on. And the IPCC concluded in the latest report that coastal flood damage will increase at least tenfold by the end of the 21st century, and even more with current adaptation and mitigation. So you have to do a lot more adaptation and mitigation to even limit the damage to a tenfold increase. And it becomes an existential threat to many coastal communities. So another aspect of climate change and the ocean is the fact that the ocean takes up about a quarter of the CO2 that we emit, and that forms carbonic acid, leads to ocean acidification, and it threatens a lot of microplankton, calcifying organisms like these, where on the left you see what a normal one looks like, and on the right the kind of corrosion you get if the ocean water is too acidic. And this threatens the marine food webs. I'm not really giving a biology talk, that's not my field, so I'm just briefly flagging this ocean acidification problem, which in my view alone would be enough to stop emitting carbon dioxide as fast as we can, even if it didn't cause global warming as well. Tropical cyclones are very much in the news today again, and we have long predicted that tropical cyclones will get stronger with global warming. That's again basic physics, because the energy source of these storms is the heat stored in the upper ocean, which is released to drive these cyclones. And it has long been debated and wasn't easy to determine whether we already see an increase in the intensity of the tropical cyclones because of data quality issues. The observation systems have improved all the time, also with the advent of satellites, so that in the earlier periods, entire storms might have been missed because they were only out at sea, never got anywhere near land, etc. So before satellites, you may not have even known about them. And that's why the data, although they did show a clear increase, they were always debated whether this is a real increase or just an artifact of improving observation systems. But in the meantime, it has been really demonstrated convincingly that there is an increase in the intensity. A study a few years back, the reference unfortunately is missing on this slide, showed that if you look at the strongest storms in the satellite record in these 8 different regions, that the strongest one was just in most of these, I think in 6 of the 8 was just in the most recent few years. And by random chance, that would be really incredibly improbable. And in the meantime, the satellite data have been homogenized so that since the beginning of the satellite era, all the satellite pictures have been reduced to the same resolution, etc. So it's a homogeneous data set. And this is a study by Cosin and colleagues in PNAS a few years back, 2020, which showed that the proportion of major hurricanes out of all hurricanes has increased from a bit more than 30% to nearly 40% over this 35-year period. So this kind of demonstrates the effect expected and predicted by physics that tropical storms are getting more intense because of the bigger energy source. There are also other studies showing that they intensify more rapidly, as has in fact happened with this current storm Ian, that they dump more rain. This is, of course, another aspect of global warming, that the atmosphere, when it's warmer, can store more moisture and rain it down. It's a Clausius-Clapeyron equation known since the 19th century. And so the expected effects of increased tropical storm damage are all happening now as predicted. And you can just go on Twitter, you see nice movies of the storm surge hitting Florida right now. Now, one of my main research areas going back since the early 90s actually has been the Atlantic meridional overturning circulation, or Amoc, which is shown here, where you see in red the surface currents that tend to generally move northward here from the tip of South Africa through the Caribbean and right up into the Nordic seas. And then here in the northern Atlantic, the warm currents give off heat to the atmosphere. They cool down then the waters and then reach a density where they can sink down to a depth between 2,000 and 3,000 meters into the ocean and return as a deep western boundary current shown in blue here going to the south. So that works like a central heating system. You have warm waters moving north, cold deep waters returning back south. And so there's a huge northward heat transport associated with that, even through the South Atlantic, by the way, which is anomalous in the sense that in the South Atlantic it's the only ocean region which is transporting heat from high latitudes towards the equator, which is a little bit counterintuitive that you move heat from cold to warm in this sense, but it does happen because of this overturning circulation with the warm surface currents moving north and the deep cold current moving south. And we know from the history of the Earth climate, from abrupt climate changes during the last ice age, for example, the Dansgaard-Oeschger events and Heinrich events, that this ocean overturning has been quite unstable and has gone through abrupt changes. And already since the 1980s, there have been warnings that it could be destabilized by global warming. And last year there was a nice New York Times article about this, which is really great online animation, graphics, etc. included. It's worth looking at, which talks about dramatic dangers. And yeah, this is just another depiction of that. One indication of what's happening is when you look at the predicted changes in global surface temperature. This is from an earlier IPCC report from 2007. You see the globe warms everywhere except in the North Atlantic. Here's the so-called warming hole, where there's almost no warming. That's in the models, that's predicted. And in the prediction, of course, we know why that is. It's because of a slowdown of the Amoc, which brings less heat into this region, and that's why this hardly warms. There's also observational data. If you just look at the observed sea surface temperature trend since beginning of the satellite era in 1993, in this case, you see that there actually has been a sizable cooling in the northern Atlantic south of Greenland and Iceland. Yeah, so it's not even just a warming hole, it's a real cold blob that has developed there. And again, this is entirely what's predicted. If we look at the climate model and look at the ocean circulation in the climate model, this is the one from the Geophysical Fluid Dynamics lab in Princeton, which has a beautiful ocean circulation at very high resolution. You nicely see the warm Gulf Stream in red moving along the Florida, North American coast. It leaves the coast at Cape Hatteras then becomes dynamically unstable and forms these meanders, etc. This looks really just like it looks in animated satellite data, but it's a model simulation from a climate model. And when you have such a climate model, you can subject it to a CO2 increase in the atmosphere, typical global warming experiment, and that has been done with that model. And the resulting sea surface temperature change pattern is shown here. And there the global average warming has been subtracted. So everything that is blue has warmed less than the global mean or even cooled. And everything that's red has warmed more than the global mean. And you see a very peculiar pattern in the northern Atlantic here in the model simulation. You have this cold blob here south of Greenland, as kind of expected from a slowdown of the Amoc, but you also have very strong excessive warming along the North American coast, and it turns out that this is also a result of a slowdown of the Amoc, and has to do with slightly more esoteric physics, namely vorticity conservation on a rotating sphere, but it's a well understood phenomenon that where the deep western boundary current crosses under the Gulf Stream there, when this whole thing slows down for vorticity conservation reasons, the Gulf Stream actually moves north, and this is what is causing this excessive warming near the North American coast. That's been shown in a suite from basic conceptual models to high-resolution general circulation models like this one. And my student, Levke Cäsar, PhD student, spent some years compiling all the global sea surface temperature measurements since the 19th century and calculated the observed trend. And of course, that picture is a little bit out of focus because we don't measure at every point every year for the last 100 years. So it's kind of a question of averaging and smoothing, etc., a bit of a fuzzy picture, but I think you will agree that this pattern here with this cold blob and this warming here near North America looks really a lot like this one, and on the right-hand picture we know it's a fingerprint of a slowdown of the Amoc, and we argue in this paper in Nature that we are observing this slowdown here in this fingerprint pattern, and when you calibrate this with the model simulation, you conclude that the Amoc must have slowed by about 15%, and it really starts to take off around about 1950s. We can also look further at changes in the Amoc further back for more than 1,000 years. Here we have simply compiled studies from the public literature which have tried to reconstruct the Amoc strength, and this left-hand column here shows various studies like that. The light blue curve is the one that we derived from the observed sea surface temperatures in 2015 in a paper. And you can see that the various other proxy series superimposed there with different methods from different regions. These are the locations of all the proxy data that were used. They all tend to show this unprecedented decline over the last millennium. And there's been a discussion of how well do these proxy data reconstructions agree in recent times with more modern observations, and we showed that in a paper published earlier this year. At the top we have the direct measurements that only started 2004. Then there's a couple of data-based reconstructions with the help of models, model data assimilation, and the three bottom ones are the three different types of proxy data, and I would say by and large they actually are pretty well consistent if you account for the time leads and lags that are involved in the different types of studies. Like if you look at ocean heat content, obviously it's lagged to the strength of the Amoc because it takes some time for the heat content to change when the heat transport changes. Now, one aspect of this weakening is freshwater input from the melting Greenland ice sheet, as has been shown in this study by my colleague Klaus Böning from Kiel. And I just want to flag that this is probably not the main reason, but it is a reason that has often been neglected, is that because many climate models don't have an interactive Greenland ice sheet, and so they neglect this Greenland meltwater component, but it is a non-negligible contribution here. Now, in terms of the impacts, we often get asked about this. Some of you might have seen the film The Day After Tomorrow. This is definitely not the impact of a slowdown of the Amoc, but of a complete collapse within weeks, which is not going to happen. This is not the realistic timescale. This is a real data analysis of the impact of this slowdown, the cold blob that is sitting out there, which, as I said, we estimate is about 15% slowdown. And what it does is, the cold blob, of course, is out of the ocean. It doesn't extend over any land areas. So the idea that the land cools is not wrong, but only when the Amoc totally stops, and then this cold blob will expand greatly, and it will probably expand over northwestern Europe, like Great Britain, Scandinavia, might really get colder. But that's not the situation we have until now. Now we have a cold sitting out of the ocean. What does it do to the air pressure? It tends to form a low pressure, like this study by Aurélie Duchesne and colleagues has shown here. This low pressure then gets this counterclockwise atmospheric circulation that is kind of preferred by the cold blob sitting there, and it brings air from the southwest into Europe. That, of course, then is hot air. So there is a great correlation between heat waves over Europe and the cold blob sitting out there in the northern Atlantic. And in fact, it has been shown in a recent study by my colleagues from another department at the Potsdam Institute that Europe is a hotspot of heat waves, and the amount of heat waves has been increasing 4 times more than in other areas on similar latitudes. And this cold blob out in the Atlantic may be one of the reasons. Now, one big issue is that the Atlantic overturning circulation has a tipping point. This has been already shown by Henry Stommel in 1959, I think, in a paper. And I worked on this as a postdoc. This is the first thing I did after my PhD in the early 90s, and showed in a 3D ocean general circulation model that you have this kind of bifurcation structure. On the x-axis, you have freshwater going into the North Atlantic, which will weaken that overturning because the freshwater dilutes the density and therefore makes it harder for the water to sink down there. And if we are on the vertical axis is the strength of the overturning, and we are somewhere here along, nobody knows exactly where on this diagram we are, but maybe in this bistable regime. And we know because of positive salt transport feedback, this curve turns back on itself. It's actually a parabola, and you have this typical saddle node bifurcation here. It's very familiar for nonlinear dynamics experts from physics. Lots of systems have this behavior, and that's a classic tipping point. So when you add more and more fresh water, you move along this line until you reach the bifurcation, and then you fall off the cliff, and the further development, the total breakdown of the overturning will become inevitable, and that's what we call a tipping point. And I was actually attending 2 weeks ago a big tipping point conference in Exeter, which kind of gave the latest on how close we are to various tipping points. There's also been a review appeared a few days before the conference in Science, which concluded that between the 1.5 degree warming and 2 degree warming, so if you call that the Paris range, we will likely exceed 6 tipping points of the climate system. So the best estimate tipping point is between 1.5 and 2 degrees for the Greenland ice sheet, for the Western Arctic ice sheet, for the Amazon rainforest, for methane release, and a couple of others, corals, for example. Here's an overview diagram, a commentary we published in 2019 in Nature, which shows again various tipping points of the climate system, some of which I've just mentioned, and it focuses on these arrows, and also the conference talked a lot about these arrows because the interactions between these tipping points are the real research topic right now. Simple example, if Greenland melts, past its tipping point. Greenland may well be already past the tipping point of complete ice sheet loss, where 7 meters of global sea level rise would be programmed in. Then all this fresh water will slow down the Atlantic overturning and can push it past its tipping point, and so on. So these tipping points are actually connected. And we might be approaching a global cascade of tipping points where one triggers the next, like in a row of dominoes. So one system which has probably passed its tipping point are the coral reefs. They have a critical temperature threshold where they bleach when it gets too hot in a marine heat wave. For example, Great Barrier Reef in 2015, 2016. Bleached coral then tends to overgrow with seaweed, etc., because it can't defend itself against that. And if you look at where the Great Barrier Reef has bleached in various years, this matches very strongly the temperature anomaly, proving that it's really the temperature that does it. It's not yet the acidification issue that I mentioned, which in the longer term really threatens the survival of coral. It's not local pollution, runoff from agricultural waste or whatever. It is actually the temperature, because every time where the marine heat wave was is where the reef bleached. And this is not just the Great Barrier Reef. In 2015, 2016, the blue ones were the only reefs of 100 that have been monitored which escaped bleaching. So we're in the middle of the death of the coral reefs, basically, which has also long been predicted. And the IPCC found that with 2 degrees warming, basically we will have no coral left. And with 1.5 degrees warming, we could save between 10% and 30% of the coral reefs. So this is one important reason why we really should aim for the Paris ambition to limit global warming to 1.5. So to conclude, global warming is unequivocal, it's ongoing, we all know this. The impacts are not subtle anymore, they are being felt around the world, and as we speak, of course, we have one hurricane and one typhoon going on, having major impacts on land, for example, and we know the impacts are enhanced by warmer oceans. The physics, biology, and chemistry of the oceans are being changed right now in a major way, and we need to stop this as soon as possible. So the IPCC has said to have a chance to stay below 1.5, we have to cut global greenhouse gas emissions approximately in half by 2030, and that is only 8 years away now. So basically every year counts. We cannot tolerate any delay, people trying to say, well, now we have a whatever Ukraine war, so let's wait with global warming policies. They are needed right now, and it's a very hopeful sign that the Biden administration in the US has passed powerful legislation to cut greenhouse gases. We have the European Green Deal, which is also a very big, good step in the right direction, and must not be slowed down or watered down in any way. With that, I think I'm exactly in my time limit. So thanks very much for your attention, and we have enough time for questions. Thank you very much.